ecosystem services refer to any of those benefits that we as people obtain from ecosystems. And these benefits are derived from both the structure and processes that are inherent as part of these ecosystems. Generally, I'll just tell you about them since my list didn't quite show up. But so they're generally grouped as regulating, provisioning, or cultural services. So regulating, I think this group here, we're probably particularly interested in those functions that would be associated with regulating the quality and quantity of our water sources. But you can also have functions in terms of climate, be it at a microclimate or a global scale, as well as a few other features there. Provisioning, of course, all the food, fiber, water that we get comes essentially from ecosystems. And then there's the cultural services, which are some of those more intangible, a little bit harder to quantify, but still very important, having to do with aesthetics, educational, and other cultural opportunities. So all of these are underlain by biodiversity, which some people value, some maybe don't, but essentially all of these services are supported by the biodiversity in our ecosystems that are cranking along some of these supporting services such as nutrient cycling, soil formation, and things such as that. And so the reason we're interested in these from a low impact development is that essentially these are engineered ecosystems out in our landscape. And so, of course, we're designing them and engineering them to serve those hydrologic types of services, but really there's opportunity for that whole suite of ecosystem services. And so we are interested in looking at, well, how much of those other services can you get out of these types of systems? And this kind of goes in line with kind of where we are, what we've been thinking about. I know initially as in the stormwater world, we kind of started with a singular focus looking at peak flows, so one of those hydrologic types of functions. As we moved along, we started getting, I know some of the work Alan Davis did, for example, looking at water quality, and we realized we really need to be managing the quality of our stormwater as well. And now as we move into the future, we're really broadening our view and looking at this green infrastructure, low impact development as an opportunity to really enhance kind of this whole suite of ecosystem services that otherwise are often lost in our built urban ecosystems. And so I'm going to focus on just a couple of these for this talk. I'm looking at is carbon sequestration all the way, and then as well as some of the biodiversity aspects of a couple of specific green infrastructure systems. So you could apply this to any type of system that you're interested in. Where I was in North Carolina, kind of the business as usual stormwater model was to put in a pond at the end of the pipe and take care of that peak. But North Carolina was a great place, or there were a lot of natural wetlands there, and so that was kind of a stormwater model that was developing, was out of a constructed stormwater wetland as a lower impact way of mitigating some of those runoff effects. And so we looked at carbon sequestration and biodiversity aspects of these two types of systems to kind of compare a conventional with a more lower impact development scenario. We also had a hybrid of these two systems, which was a pond in which a vegetated littoral shelf had been either constructed intentionally or had developed over time as that pond filled in with sediment and got some plants established around the perimeter. So we looked at 20 ponds and 20 wetlands across the state of North Carolina. And when we set up our biodiversity and carbon sequestration surveys, we were looking at all of those hydrologic zones that are characteristic of a stormwater wetland, so kind of your temporarily or drier area around the perimeter, then a shallow water area that's got those emergent macrophytes, and then an open water area where you have open water. That's most of a pond in a pond system, or about 30% or so in a wetland system, at least per the North Carolina typical design. So in terms of biodiversity, we're interested in looking at whether or not stormwater ponds and wetlands support different levels of biodiversity. We looked at this both in terms of the plants as well as in the aquatic macroinvertebrates as kind of an indicator of the overall diversity that that system was capable of supporting. And so in terms of vegetation, we found that stormwater wetlands had significantly higher vegetation diversity. This is perhaps to be expected if you think about how these systems are designed. A stormwater wetland is intentionally planted with species appropriate for wetland environments, whereas most of the ponds that we looked at were not. They were either mostly turf or some of them had colonized naturally. And that's where the plants were coming in. And so we decided that it seemed to be the case that in those systems that had colonized naturally, they tended to have the lower diversity because they were being colonized by more aggressive types of plants. So, which is good, I think, from in the standpoint that in the design you can maybe direct that diversity by jump-starting it. For instance, in a stormwater wetland, by planting kind of taking from a palette of different emergent macrophytes, but something that's not, say, cattail that's going to take over your system if it's not. Well, you just don't need. There's no need to plant cattails, at least in North Carolina. They'll come on their own. In terms of macroinvertebrate diversity, I was surprised in ways that ponds supported a similar level, if not even more diverse aquatic macroinvertebrate communities. But when we looked at sort of the mix of those types of insects and that were in there, we did see some differences when we broke them down, looking at kind of the functional feeding groups. So just in general, we are looking at so macroinvertebrates that are grazers, so eating primarily paraphyton in these systems, collectors such as mosquito larvae or midges feeding on kind of the detritus, shredders that are breaking up larger pieces of organic matter, and then the predators, which are feeding on any number of those guys. And so in a populated environment, we really think it's positive to have some of these predators, so you can potentially be keeping down some of the more nuisance species, particularly mosquito larvae, which were, okay, so first I'll just say you can see there's not a whole lot of difference between a wetland and just all the ponds grouped together, although we did tend to see more mosquito larvae in the ponds, and whether or not that was just luck or the fact that we had good predators, not for certain. But when we did look, again, separating out these ponds with and without the littoral shelf, we saw significantly more of those predators in the ponds that had a littoral shelf or had some of that vegetation. And a lot of those predators come or are cued to come and leave their offspring in these systems by the presence of plants. And so, there have been links drawn between that. So it was nice to see that in our little field study here. And again, we think that this is a way of building in a more desirable mix of macroinvertebrates, so you can provide some of those pest control regulating services that are part of a well-functioning ecosystem. In terms of carbon sequestration, we approached this question using sort of a space for time substitution approach. So we didn't know the starting point necessarily of each of these 20 systems of our ponds and wetlands, but by looking at the system age and the relative amount of carbon in those systems, we tried to draw some conclusions in looking at whether or not these systems were accumulating carbon with time, thus serving some carbon sequestration function. So we sampled and got the soil carbon content in our soils from each of those hydrologic areas, and then by measuring the soil bulk density, we're able to come up with a mass of carbon per unit area, and then regress that with the age of the system to see if there were any relationships there. This is just to show you the raw carbon stock, so not looking at any time function here, but you can see that across the board, no matter which of those hydrologic zones you're in, the wetlands have significantly higher soil carbon. This is, again, similar with the plant biodiversity. These systems are starting at different points per the way that they're typically designed in North Carolina, where the recommendation there is, since you're putting in plants, making that investment, you want to start the system with some organic matter. So a lot of these stormwater wetlands that we were looking at had been amended with soil organic matter somewhere in the tune to probably 800 to 1,200 grams of carbon per meter squared was the general recommendation. So what we're seeing here is that, well, yeah, there's more carbon, but they started with more carbon, so that's what it is. But when you look at it over time, what we saw was that there was, at least for the shallow vegetated area of wetlands, a significant actually relationship between the amount of carbon in the system and the age of the system. And so by looking at the slope of that line, we are predicting that we're getting about 85 grams of carbon per meter squared of our wetland systems. So this can be pushed as we, they just released the latest IPCC report. Things aren't getting a lot better, but if we can start looking at these constructed ecosystems as a way of sequestering some of those greenhouse gases, we can promote them as there's just an additional benefit that they're providing. Again, we looked at our ponds with and without that vegetated littoral shelf. And again, it looks like we have, although not perhaps strongly significant, but there is some relationship in actually a similar slope you see here. So looking at a similar rate of carbon sequestration in those pond systems, at least in that vegetated perimeter, where they are sequestering carbon at a rate similar to what we measured in the stormwater wetlands. So another little benefit that we can see with that vegetated littoral shelf. And this is just to give you an idea of how our study compared with some other, not necessarily stormwater wetlands, but some constructed or recreated wetland restorations. So we are kind of on the low end, but that could be a regional difference as well, as you see where some of those locations are. So just to summarize this part, I think that looking at kind of this broader suite of ecosystem services just gives us another kind of talking point for promoting some of these different LID practices. Especially with the case of that littoral shelf, I haven't seen any studies anyways where they've been able to really bear out that a vegetated perimeter necessarily gives you better water quality, but we can definitely see some other benefits or reasons for doing that in terms of biodiversity, perhaps pest control, and then the carbon sequestration aspects. So again, I hope this is something that as we move into the future, we continue to look at some of these other services, not just trying to quantify them as we did here, but as some of the other talks you've heard earlier, looking at social values associated with those, and really starting to make this a stronger piece of how we try to bring in the design as well as promoting these types of systems and assessing their performance. If we have a little bit of time, I'm going to talk just a little bit more about this carbon aspect of these systems, and putting that into the context of carbon emissions associated with these systems. So I think you need to look at both sides, right? Both the ecosystem services as well as potential ecosystem disservices. And this is really, we did this work with the wanting to find out if, even though we have carbon sequestration probably in any vegetated system, is the way that we construct it, we source the materials, we maintain it, going to actually cause so much more carbon emissions that we aren't really getting that carbon benefit. And so what we did for this is we just developed kind of a simple model using basically a lot of information from the literature to compare the carbon footprint among different stormwater control measures, SCMs, that's that acronym there, which includes a lot of our LID practices and what we would consider green infrastructure. So yeah, so these are the practices on which we specifically focused on kind of most of the whole gamut of things, as well as looking at some of those different conveyances, whether you're using a grass swell in a more LID type of situation or a more engineered concrete channel or reinforced concrete pipe. So the general conceptual model associated with this, coming up with this carbon footprint, is to look at the whole life cycle. So first you've got the carbon that's embodied in those materials, right? So if you're building a bioretention cell, that sand came from somewhere. So there's a carbon cost associated with the extraction and then transport of that sand. Then comes the construction, which is a little easier, I guess, to think about in terms of when you go out there with your excavator and you're digging a hole for your bioretention cell. So what are those emissions associated throughout the construction? Then, of course, there's ongoing maintenance emissions, and then standing to offset all of that is the actual sequestration by the vegetation. So that's what we were trying to measure in the previous study. And so, pretty simple, actually. Those three, the embodied, construction, and maintenance emissions all add to your carbon footprint. Carbon sequestration offsets it, so you can represent it with a pretty simple algebraic equation there. So just to give you an idea, against all of this, all of these numbers are kind of out there, so we just brought them under one roof to be able to predict a carbon footprint associated with stormwater control measures. And so there's, in terms of the embodied carbon, we are looking at some different databases out there that have done this whole life cycle analysis and inventories. So we use those types of numbers to come up with the embodied carbon associated with those different materials that are pretty typical in our stormwater installations. We used a couple of models that have been developed by the EPA in terms of looking at both emissions associated with on-road vehicle travel, so transporting equipment to the site per se, or transporting maintenance crews, as well as off-road equipment operation, which would be your dozers and excavators and those sorts of things. And we came up, we were able to, so this is a predictive tool, so we just, for the results I'll show you, used kind of typical construction practices in order to estimate how long those equipments would be, or how long each of those pieces of equipment would be operating, and then those emissions associated with that. In terms of carbon sequestration, there haven't been, again, a lot of studies looking specifically at LID components or stormwater infrastructure. So where there wasn't that, we just used values for representative vegetated ecosystems to try to get an estimate of how much carbon we could sequester with these types of systems. And so this graph is just to show you, really, for all of these systems, the majority of the carbon emissions are at the beginning, and primarily in the carbon that's in the materials we use to construct these. And so I think that what this points to is that in terms of a carbon impact, if we take a look at where we're sourcing our materials and even the types of materials you can use locally, that could really decrease this net carbon impact. Because you can see that because it's so large at the beginning, we really kind of start in a place where it's hard to offset that with just vegetation. And this can be done, again, looking at the balance through time between carbon sequestration by the vegetation versus what you are emitting through your very necessary maintenance to keep these systems functioning. And so this is just to show you through time what we were projecting for, giving again this example of a pond and a wetland, and using the rate of carbon sequestration that we used, and then assuming that the maintenance was the same, you could actually have a net sequestration benefit with the wetlands. This doesn't account for methane emissions, which we didn't measure, and that can vary pretty wildly. So if you consider that, maybe it's not going to be, maybe you'll not have a net carbon benefit. But regardless, you're probably better off with a wetland than a pond in terms of long-term carbon emissions. This is just to show you the rest of those other systems that we looked at. The green roofs and permeable pavement I didn't put on there because they were way, way up there, and there's not an appreciable amount of sequestration that happens in those systems. But you can see kind of from bioretention, rainwater harvesting as a RWH, ponds, level spreader, vegetative filter strips, wetlands, like those are all kind of our lower carbon options, I guess, that are out there. And these were just using, this was come up with using kind of standard assumptions. So again, these are, this type of tool could be used to try to look at some of those different factors that are coming into a carbon footprint. And we talk about optimizing the system design for water quality and quantity. Well, maybe on the side we can start bringing in the carbon aspect of these systems. This is just for the conveyances, and it's pretty obvious a grass swale is the way to go if you want to save on carbon in these types of developments. So just to wrap up with in terms of looking at carbon sequestration, both in terms of vegetative sequestration and then the offsets from our maintenance and construction, most of our, at least our engineered green infrastructure is going to be a net carbon source in the environment. But there are some potential, again, as we keep moving forward and keep improving the way we design these systems, to design a lower carbon system that also still functions for that water quality and quantity benefits. And so again, as we move ahead, I think this is really an area where we'll continue to explore, looking at kind of this broader suite of ecosystem services and how we can design these systems to provide a more optimal suite as we begin to appreciate some of these other functions that our green infrastructure and low impact development practices can provide. And so with that, I will conclude, and I'm right on time.
We have time for one or two questions.
Yes?
Yeah, I'm with the city of Broken Arrow here locally, and I reviewed a lot of wet detention pond designs over 20 years. And 20 years ago, they were just flood control. 10 years ago, we started looking at stormwater quality. Now we're looking at biodiversity. Has there been any kind of national studies that really look at those three items as an economic, and then even, I think, even have to throw in aesthetics and even recreation into the mix as well? I mean, wet detention ponds are so common throughout the country. Is there some kind of a way to get your input more involved in the design of them? And that's the challenge I'm looking at, is trying to get the biodiversity and the other functions of them kind of in the forefront as they're designed. I mean, what's your opinion on how to get some of that rolling along, I guess?
Well, so where we are is, I think there have been, kind of maybe a few studies. I know the EPA has done some stuff looking at the property values. So I think that's what we need now, is helping people conceptualize a dollar amount, because just talking about, well, you get more dragonfly larvae.
It's hard to put a dollar amount on it, but if you have a nice trail around it and someone that lives there walks around that pond every day,
and that's a good point too.
I mean, it really does have a benefit.
I think incorporating the very obvious recreation features, because that's how you get people there, and honestly, people probably value that more than anything else. So, yeah.
So you looked at 20 ponds and 20 wetlands? So there were 40.
Yes.
And those were all built all over the state, different places, right? And what was the average size of those?
So probably like half an acre was probably pretty typical, at least for the wetlands, and sometimes larger on the ponds. But all of them were under an acre, mostly.
And did you find any difference in the species diversity based on the size?
I'm sure I looked at that. It wasn't significant. But I didn't, I can't remember exactly, but I can find out.